is Sylvie Méléard from the École Technique. She will give a sequence of lectures. And so I don't know if all of them, or the first one will be called Interplay between scales for eco-evolutionary mathematical models.
No, it's a global title of the course. So thank you very much for the invitation, even if I know that I replace. So I will try to be at the level. So thank you. And so first of all, so I would like to present you some recent work concerning different scales we are playing with. There are different co-authors. So Vincent Calves, that you know, Nicolas Champagnat, and Sylvie Méléard and Viet Titran. So they are in researchers in France, either probably in probability or in PDEs, and three biologists. So Sylvie Méléard and Régis Ferrière are more involved in evolution and ecology and relation between evolution and ecology. And Myriam El-Karoui is a biologist, is really an applied biologist, I could say. Régis and Sylvain are more theoretical biologists. And Myriam is really involved in the study of bacteria and the bacterial resistances to antibiotics. So the models were more or less inspired by their questions. So I give you a short outline of the course. So in this course, I would like to develop some mathematical models that can keep track of the effect of a very small subpopulation in large population approximation. And so I will try to firstly to explain you the biological context and through different eco-evolutionary problems, more or less theoretical or applied. And so the basic tool is what I call an individual-based stochastic process. And so I will first explain this process, but it's now relatively standard, and the large population approximation, so the relation between stochastic processes and nonlinear PDEs, so either integrodifferential equation or real PDEs. And I would also introduce what was called by Dawson and Perkins historical processes, which is a process which will take into account the lineages of the individuals, and that we have already studied in the past with Viet Titran. And I will show you, so in one context, the relation between these historical processes and the spine approach as studied by Hardy and Harris, Bancet Delmas, Marcel Tran, or more recently, Aline Marguet. And we will show that on a specific application, which is to quantify the dynamics of lineages in a context of adaptation to a certain environmental change, gradual environmental change. Then I will consider some questions which comes from biological question by Myriam El-Karoui concerning the effect of the horizontal transmission in evolution. So I will show you that there are very specific long-time behaviors in such cases due to the trade-off between horizontal transmission and demographic parameters. And I will show you how we try to understand these behaviors from a stochastic point of view. And next, I will present you a very, very recent work concerning how to say, a question which was asked, I remember, by Benoît Pertan at least 20 years ago, that is a direct relation between individual-based models and Hamilton-Jacobi equation. And I will show you how it is related to this point of view of certain scaling in population size. So all this, on my point of view, are based on the modeling of adaptation and evolution for asexual populations. So that's why I'm very interested in microorganisms as bacteria or cells. it's asexual. And we assume that the individuals are characterized by some genetic of phenotype information, which will be quantified by something which will be called a trait. This trait will influence their ability to reproduce or their probability of survival. And so this information can be transmitted vertically, so that's the usual heredity property in such sort of context. And the descendants inherit from the genetic information of the ancestor, except when mutation occurs. And the mutations create some variability in the trait distribution, as we have seen. And there is also selection. And so there are, in these eco-evolutionary models, there are two sorts of selection. First, if you have individuals with a higher probability of survival or to reproduce, a better ability to reproduce, then they will invade the population in a certain sense. And that's a selection from the population genetics, we could say. But there is also a selection which comes from the ecology part of the model, that is the competition between individuals. That we will mix both the 2 points of view in our model. And the next thing here is in the second part of the talk, we will add some horizontal transmission. I will explain some example of how bacteria transmit some information during their life. And we will see how it can change the evolutionary outcomes. So why I'm speaking about scales is because we have different sources of randomness, but they are not at the same level at all. So you have randomness as a mutation, the molecular level, when you have DNA replication. There are a lot of mistakes and implying some different outcomes. And you have also randomness at the individual level, that means in the demography, for birth, death, contact, when you have contact, movement, etc. And you can also add some environmental variation, which are another level. And so that you have different size scales and time scales. And it's really fascinating in this work to play between all these scales. And depending on the scale, the assumption you have, you can obtain very different mathematical objects and understand in which case you can use such sort of mathematical object or such other sort of. So the first question we will be interested in is the adaptation to a gradual environment. So that's questions we had with Vincent Calvez in particular. So that was the question was as follows: you live in some place, and it seems to you that some population is at equilibrium. But of course, imagine that the environment is changing. You are in the moving framework. And so the population seems to be at the equilibrium, but in fact, it is adapting, but in a certain way that for you, the population seems to be at equilibrium. So that means if you consider your population, the distribution of your population concerning some trait, for example, during certain time, it seems that you have a distribution which is always the same a long time, but in this moving framework. But if you fix some individual at time t, you can ask from which ancestors they are they are coming from, and we would see that in fact, if you consider the ancestor of all these individuals alive at time t, they are all, it's a very few number of individuals, and they are all in the tails of the distribution. And so that can be important to have that in mind, especially in agriculture. And so the question is how to model this response of the population to the gradual change of environment, and how to capture the dynamics in the paths of the lineage of an individual chosen at random. So the second question we have in mind concerns the dynamics of resistance to antibiotics. So that's a question we have with Mariam El-Karoui. So when and is interesting on genes, resistance, the genes of resistance, which are carried by plasmids. So plasmids are very small DNA, very small DNA strands, which are circular DNA parts, and which are in the bacteria, in the cell, independently of the chromosomes. And they can be transferred by contact, exactly in this way. So you have really a picture, an electron from an electronic microscope. And so you see that when a bacterium, so carrying the plasmid, encounter another bacterium, so it can develop some arm called pilus. And so with this pilus that you see here in this picture, so the two bacteria are in contact, and then one strand of the DNA of the plasmid is cut and goes through this pilus to the other bacteria, and immediately you have a second copy of this DNA filament. And so you have, with this way, you have really an exchange of information during their life, of a bacteria during their life, and it's an exchange. There are other genetic information transfer in between bacteria, but this specific transfer is by contact between the bacteria. Of course, if a bacteria carries a plasmid, that it's costly for. And when I say one plasmid, in fact, one plasmid corresponds to a certain number of copies of the plasmid. So you have plasmid with 20 copies, plasmid with 200 copies, and so on. And of course, it's very costly for the bacterium. She needs to allocate some resources to survive and with this plasmid. And so there is a trade-off between the demographic properties of the bacteria and the facts to carry the plasmid. Remember, so if you have in an antibiotic medium, the plasmids are carrying the gene of resistance. And then we can ask the question, how is it possible that bacteria carrying plasmid are not eliminated in the population by evolution? Why are they the time? And secondly, I will show you very amazing simulation show in specific cases, but when you can observe that you have a population which has almost condemned to be extinct, but so we are in some long time behaviors for population. So you have some strains which of population, so condemned to be extinct, but there are a few individuals which are remaining here. And when this big population is almost extinct, you can observe new strains which appear, and almost periodic strains, in fact, in this picture. And so I will explain you how we try to understand with stochastic tool such sort of behavior. So that was the introduction. Now I will briefly summarize the basic tool of our approach. So as I said, we are concerned by the modeling of asexual populations, which are structured by some traits. So X will be either a real number or a vector belonging to a subset which can be compact or not of R or RD. And so we will consider a generalized birth and death process, and with mutation, competition, possibly horizontal transmission. And in such sort of model, of course, the population size is not fixed. We have a scaling parameter, capital K, which will be the order of magnitude of the population size. And equivalently, we can see also that as the carrying capacity. That means the amount of available resources, okay? And that will be our scaling parameter in all the talks, during the talks. That's the main point. And so we will consider the population process will be a measure value, the finite measure value process, which will be defined on R plus, on compact interval in R plus, and which is defined as follows. So that's very, very simple, and we have already seen, and I suppose that before I arrived, you have already seen such sort of process. It will be renormalized by K, so 1 over K, to see something, because K is the order of magnitude of the population, and K, so we have said that we will be in large population approximation, so K will tend to infinity. And we consider the sum over all individual alive at time t of the Dirac measure on the trait of this individual. So there are different ways to label this individual. So here we will take, for example, you can take I in the what is called Ulam-Harris-Neveu labeling, which consists in the fact that the label of the individual is a concatenation of the labels of the ancestors. And so first we will consider some modeling for this adaptation to a gradual environment. And so here I assume that the trait is a real number. And so I will take a very simple model, but because that's a miracle of Gaussian framework, we will have explicit computation. And I will say at the end how we can generalize this. So I suppose here that the birth rate is 1, and that, so it's a quantitative genetic point of view, that during the lifetime of an individual, the trait is moving following a Brownian motion with variance sigma square. And so it's an it's what's called an infinitesimal model, that you have an accumulation of very small mutations that is modeled by a Brownian motion. And we assume, so that's a way to model the gradual environmental change. We assume that the optimal trait here will be moving and will be sigma ct. So c, in a certain sense, is the speed of the environment. And you assume that the optimal trait will follow the environment, sync to temperature, for example. And then the individual, the intrinsic death rate will be x minus sigma ct square over 2. The over 2 is just to obtain beautiful formulas, exactly as this sigma here. Okay, that's the size of the typical size of the mutation. And we will add competition, and here we will take some simple competition logistic death rate. That means that if the population is of size n, but you remember, n is moving all the time in continuous time, the individual competition death rate will be n over k. And so as I said previously, I will first consider the population process defined like that. So of course, insert sort of formula. So I will write in either for a good test function f, zkt of dx. That will be, I will also write zkt f, that depends of the place I have on the right slide. And it will be trivially equal to the sum over all individual alive at time t. So nkt is the population size of f of xit. So very simple measure. And so here we are able, I will write it for a second process in 2 slides, but we can explicitly, pathwisely define this process as solution of a stochastic differential equation driven both by Brownian motion and by Poisson point measures, okay? Describing all the probabilistic events we have for this process. And so we can prove that depending on the good initial moment assumption, this measure valued process is solution, so in a certain sense, of is a semi-martingale, in the sense that for any good test function f, then the integral of f with respect to this measure zkt is a semi-martingale. And we have an explicit, well, so here you recognize the growth rate. So you have the birth rate, the intrinsic individual death rate, the competition part. And here you have the term due to this Brownian motion between the genes. But remember, here when we write the process in this way, we consider we are in the fixed environment, and we look for the effect of the environment. But now look that we are in the moving framework, okay? And so we will change the measure, and we will consider the good process will, for the good, for this question, the process we are interested in is the image measure of this process by the function which to x associate x minus sigma ct. Okay. And then in the moving framework, I will consider this process where you see what is changed. Now we have x squared over 2 here, but we have an additional drift term. Okay. And so the operator which appears now is the infinitesimal generator of a drift-on Brownian motion. Since you have this second derivative here and the first derivative. And so it's easy to prove that under the moment assumption I have written in the previous slide, that you can write the process in this form, and that nkt of f is a square integrable martingale, and you have the expression of this its quadratic variation. And we can observe that if you can control the moment, if you can control this expression, here you have a 1 over k in front of this quadratic variation, meaning that when k tends to infinity, the martingale part will tend to 0. Okay, so it's stochastic. You see that for large approximation, for large population approximation, we can hope to obtain some deterministic limit. So we have in a sort of a law of large number context. Okay, even if we have non-linearity, and the non-linearity is here is the total mass is the population size. ZKT1, it's also what I wrote NKT, it's a population, the number of individuals, sorry. I will write the exact equation we can have. So we can have a pathwise representation of this process. As I said, if you can fix, so I want to fix the probability space because I will make coupling on this space. So I will fix some point measure n of ds di d theta. So on R plus time I, which is labeling set, then a countable labeling set, and R plus, but this theta will be the way to decide if when I have a jump event, I will either divide or reproduce or die or nothing. Okay, that's acceptation rejection modeling of the jump process. And I have some independent Brownian motion, and xi will be, as we have seen, the drifted Brownian motion, corresponding to this drift part which arrive when I made this change of motion. So the probability space will be defined by these processes, and when I speak of martingales, the underlying filtration is a filtration, the natural filtration associated to this set of Brownian motion plus the Poisson point measure. So the first remark, so it's relatively standard, is that if we have good initial moment assumptions, that uniformly you have a moment de plus something for the total mass of the process, and we also need to have a control because of this death rate of some the integral of x squared, some moment x squared is good with respect to the initial measure, and we assume that uniformly in k it's finite. So when we have this assumption, one can prove that's essentially standard, that you have a propagation of this moment assumption on any finite time interval. Okay, so uniformly in k, you can prove such sort of property uniformly for t in any zero capital T. That's why we will work on finite time interval for the moment. Okay, and so we can prove that under this assumption, if we also assume that the initial measure Z0k converges in probability to some measure, to some deterministic measure. So I write V0 x dx, but in fact here you don't need to assume any density for this initial measure. Okay, so we can prove that the process Zk, the sequence of processes Zk, will converge in probability and in L2 to some deterministic function of t and x. And here we have really, so you have, in fact, you have a measure, Vt of x dx. Here we have a density, and which is a unique non-negative weak solution of this partial differential equation. So it's you have a term of order 0, which corresponds that here you have the growth rate, and you have this operator corresponding to the drifted Brownian between the jumps. Okay, so that's a PDE point of view from this equation. Mention that in particular we have this that when k tends to infinity, the expectation of the supremum for t less than capital T of the integral of f with respect to zkt minus the integral of f with respect to this measure v of tx dx, this difference between square, the limit is equal to 0. Okay, so the proof is relatively standard. So that's a compactness uniqueness argument. So the compactness is obtained by proving the tightness of the sequence of laws, and that were essentially due to this propagation of control on the moment. So I have mentioned, and so perhaps I could say a few words of the. So you can prove the tightness of the laws, the sequence of laws of zk, and then it's easy to characterize the limit because of the semi-martingale property we have seen. Since you assume that the martingale part will tend to 0, you prove that correctly, and then you see that in the limit, the limiting value will be solution of an identical equation, but without the probabilistic part. Okay, so that's the weak sense of the PDE. And now you have, if you have characterized limiting value as a solution of this, we have to just to prove the uniqueness. And for example, to prove the uniqueness, a good point of view is to consider the associated mild equation. And that's a probabilistic way to prove the uniqueness, so I like it. So you take phi in C2B of R and YT. So YT is a drifted Brownian motion. And so I assume that now T is fixed and S is less than T. What I will explain is that to prove the uniqueness, we will switch to the mild equation, to the mild solution of this equation. And that means that we will consider the semi-group, essentially it's a semi-group, which is of X, which is, so T is fixed and S is less than T. So it's a function of, it's better to write it like that. That will be the expectation of phi of y t minus s, exponential of minus 0 to t minus s of the y u of square over u. So I introduce this quantity because the problem, of course, is that we have a term of order 0 here, which is nonlinear, and it's a way to obtain it, to easily obtain the uniqueness. So if you consider this, it's easy to prove. So of course, it's computation that t phi is equal. So phi is psi t tx is equal to vt psi t 0 point plus. So all the terms, I use that to in fact to cancel all the term corresponding of the derivative of v, and also by this the term corresponding to the x squared here. And so here you have just 1 minus the total mass of v, the nonlinearity, times psi t of f x ds. Sorry, dt. Something increasing. Yes, vt of very hard. I wrote it v of tx. Yes. For the moment, I don't know that it is a density, so it's a vt of dx. I will say why it is a density. So you have, of course, you have to compute how the operator here play on such function psi, and you will see that almost all terms disappear. So when we have this expression, of course, if phi is bounded, psi is bounded by the same constant, and then you can with this you can use Grunwald arguments to prove uniqueness. You take two functions and you write the expression, and they have the same initial condition, and so on. Okay. So because if not, it's not trivial to find the good space in which to prove the uniqueness. But if you consider the Miley equation, you are in the space of bounded function. It works. Okay. Okay. So that gives the uniqueness, and we have to now that remember that in the simulation I show you, we assume that in the moving framework we were in equilibrium. Okay. And so we will consider. We will see if for our equation, which is this equation in red, we have steady states, some equilibrium, and we will assume that we will be at this equilibrium. Okay. So the first question is: do we have some stationary states for this expression, for this quantity? And so the goal is to find good candidate to be solution of this expression, of this quantity. Okay. So you can see that as an eigenvalue problem, and you have an operator which is here, and here you have a term, a certain quantity alpha times f, and alpha will be has to be equal to 1 minus the total mass of f. Okay.
Don't touch this.
Sorry. So in this case, it's particularly simple to find some candidate because you have just to compute, and you can prove that depending on. I will say a few words about that, sorry. If sigma plus c square over 2 is less than 1, then you have a candidate to be positive because the question is that we want to have a positive distribution. Okay, so that's the condition for f to be positive. And there is one candidate to be a solution, which is a normalized Gaussian law with mean minus c and a variance sigma. Okay, and so you see that this minus c, in a certain sense, that describes the delay you have to follow the environment. Remember, the optimal trait is 0, but here we have a delay which is given by this minus c. Okay, and so lambda will be the total mass of f in this, and is given by the red expression. Okay, so it's easy to find a good candidate, but it's not so easy to prove the uniqueness. And so perhaps I would like to change my Bible, but I think that I not. I'm sorry, but I broke my arm. Could you help me? So I show you the trick to prove the uniqueness of f. That was that was no, it's okay. I can. That was a question by Vincent, and so that trick due. It seems to be due to Tartar, but it's Pierre Lyons who gave me the trick, and so I denote by capital A this operator, and then I am looking. So I know that I have at least one solution, which is capital F given here, such that f is equal to alpha f with alpha, but we don't need that, is equal to 1 minus the total mass of f. Okay. And so well, first remark is that if we consider not f, but f tilde, where c has been replaced by minus c. So you take exactly the same thing, but with minus c. It will be in the same way solution of this expression, but with c replaced by minus c. Okay, and then f tilde satisfies that the adjoint of A, the formal adjoint, f tilde is equal to alpha f tilde. Okay.
Can you see what was lambda? Can you please recall?
Lambda is written here. It's just computation.
Sure, but if and only if lambda is equal to what, and what was the definition?
Sorry?
Yeah, that's the definition.
Lambda will be the total mass of F. F over lambda is a Gaussian law. And you see that this alpha, in fact, will be sigma plus the square over 2. Since alpha is 1 minus the total mass of F. Alpha is equal to 1 minus lambda. Sorry, we have to play with. Okay, so we know that. We have that. And we have. So now let us consider another couple of an eigenvalue mu and a test, an eigenvector phi, such that phi is the total mass is lambda, same as F, and that phi is positive. Since we state that there is a unique positive stationary distribution that we play a main role. Okay. So we have the first trick is to prove that alpha is equal to mu. So we consider the integral of R operating on phi times F tilde. So that will be integral of phi operating on A star, the adjoint of A, F tilde, and that H star F tilde is equal to alpha F tilde. That is alpha integral of F phi F tilde. Okay, but if you write things, but in another way, that's the first point. But in another way, sorry, by assumption, phi is an eigenvector related to mu. Okay, so this is also mu phi ft, and then that implies that alpha minus mu phi f tilde is equal to 0. But phi is positive, F tilde is positive, so that implies that alpha is equal to mu. So that's the first thing. And second, so now we want to prove that phi is equal to F. And that's a trick, that's really a trick, but it seems that it works in many situations. That's why I'll show you. You take psi is equal to the square root of phi F. Okay. And you compute F psi minus alpha psi. So you have to trust me. It's a computation, easy computation. It's minus sigma square over 2 times phi prime F minus phi F prime over psi square to the third. And that there is a square. That's very important. Since here you observe that this function is negative. It's not positive. And I call this expression, I call it capital D. And the main point is that it is negative. And now I compute, as earlier, Fi times the integral of Fi times F tilde. That's psi, this one. Huh? Okay. So we have psi square of F tilde, and it's equal to as earlier, that's to alpha integral of psi F tilde because of the expression that F tilde is an eigenvector for the adjoint A star with respect to the eigenvalue alpha. Okay. Alors, then what we can observe from that, remember, we have observed that F psi minus alpha psi is a certain function D which is negative. And then if I observe, you have that give you that D psi, the D, F star, F tilde. If I make the difference give you the integral of D times F tilde is equal to 0. And here we have a positive function, and D is the sign. Huh? Okay. And so that implies that D is equal to 0. That's the main point. Okay, so what does it mean? That means that phi prime F is equal to F prime phi. And then we can observe that means that that implies that, for example, the square root of So phi, I will put phi over f. F is not null. Prime is equal to 0, and then phi and f are proportional. And since they have the same mass and they are positive, they are equal. So we have the uniqueness of the stationary distribution, capital F. So now, what does it give? And that, so we assume, so we will keep now, so all, we always keep this uniform moment assumption on the initial condition. And now we assume that when k tends to infinity, the process Z0k will converge to this stationary distribution, capital F. Okay. So what does it give now? Because so if you perhaps I forgot to write that when you consider this equation, I forgot to write that V0x is this V0x. Okay. The initial value of my PD, my solution of my PD. And so now if you take V0 is equal to capital F, which is a steady state, of course, Vtx will be equal to F all the time, okay? And then we can here replace Vtf by capital F, comma, small f, okay? Where F is a steady state. And in particular, sorry, if you take F, so that's so we have this one, this quantity, sorry, and when small f is equal to 1, so if you consider the total mass of the process, you prove that it is very close when k tends to infinity to the value lambda. And remember, why do I consider this term? Because it's a nonlinearity. And so what I am saying is that if I assume that Z0k converges to this steady state capital F, then the nonlinearity will be very close in this L2 sense, but uniformly in time on any finite time interval, will be very close to some constant. Okay? So you can begin to see the idea. Okay. So now I will speak about historical way. Yes?
Is there time for a quick question? Yeah. So you have a whole range of values now, right? For the speed that you can choose for the speed C. So there are solutions for various speeds, right?
Yes, the C, you have this constraint to obtain some positive solution.
Right. Exactly.
Okay, that's the only constraint we have.
So I assume later you will. There will be one speed which will be more important than the others.
I stayed theoretical. No.
Okay.
No, I don't go to long time behavior because I will observe individual at fixed time and come back in the past. That's my goal here. It's not to go. Okay. So now, as I said, I would like to model the lineages of the individuals, okay? And to do that, I will introduce what was called a historical process.
Just one question. So if C is bigger than this the maximal speed, can you tell us what happened to the population?
No, because you don't have, it's not the same problem. You don't have any positive steady state. So all the theory does not work. It's really a condition to have this solution. And it's really related to the fact that in this case, the alpha is 1 minus the total mass of F. No. So so as I said in the introduction, the point of view of historical processes, I think it was introduced by Dawson and Perkins, but they spoke about historical super processes in the 90s, and there are beautiful text on these processes. And so with Tran, but at least 10 years ago, we developed the individual point of view from these historical processes. And the way is that now the process, it's tend to be with value in the set of finite measure on the trait space. We will consider always a Cadillac process with value in the set of finite measure on the space of paths. okay, of trajectories. So it's a very infinite dimensional process because you have the space, the traits, the space, the path space. You have the finite measure on this path space, and you have the function, CAD-like function on this space. Nevertheless, we have good topologies, and we can do things as well. Okay. And so we consider what is hk at time t between 1 over k. You will sum on all individuals alive at time t, but you consider the Dirac measure on the lineage of the individuals labeled by I. And it stops at time t, okay? So what do I mean by this quantity? So if s less than t, we have to define xis. I is the label of the individual alive at time t. So it's very easy, and especially with this sort of labeling. So you have, I take only one individual at, sorry for the design of Brownian motion, which is not exactly, but you assume that you are here at time t, and you want to, so you have different labels. This guy is dead, and this guy also. And you want to define what is xis, and I is the individual alive at time t. So of course, so either, so you take another time s here. So either the individual was already born at time s, and then the trait is the trait of the individual at time s, or it was not born, and you take the ancestor living at time f of this individual I, and you take the trait of the ancestor at time s. Okay, that's what does it mean. Okay, and so to work with these processes, you have to choose good test functions. And so that has been developed by, for you, very old words, by Dawson and then by Alison Esrich. I think it is in course of Saint-Flour, I'm not sure. And so we will take this test function. So why now? Why? When I write x is a trait, y is a trajectory. Okay. So y is a function from R plus to R. And we consider test function phi of the form product for J is equal to 1 to m of some function Gj and on the trajectory at a fixed point. So we fix the time t1, t2, tm for any m integer number. And we take some smooth function Gj, and okay, we construct like that this test function. They are well adapted for this Brownian motion context. For the jump context, I will speak later. You have to choose other functions, okay? But here it works. And then you can construct the historical process. What is important is that it is on the same probability space that the process zk. You see that I constructed it a solution of a very infinite dimensional stochastic differential equation, but in a certain sense, here where you have finite objects, since you consider the integral of a certain test function phi with respect to hk, and it's a construct on the pathway with the same point Poisson measure and Brownian motion that's zk. So we will be able to couple things, okay? We are on the same probability space. So what are these quantities? So that the bad things that they are not so easy to play with, but just definition. So we have this function phi of y defined here. And what I denote by d tilde, so it's a sort of generalization of the derivative of phi at time s and trajectory and at for trajectory y, it's the sum from k. So phi is really this test function, and with this notation, k is equal to 0 to m minus 1 of the indicator of t belonging to s, sorry, tk plus 1, with t0 is equal to 0. And we have here first, the product for j equal 1 to k of gj of ytj. So we don't do anything on this part. But so you have a product until n. And so you have a product from j is equal to k plus 1 to m of this function gj, sorry, prime taken on ytj, okay? And delta tilde is also, it's a sort of a generalization of the second order derivative, and it's the same thing, except here you take a second derivative of this function, okay? So it's, and you have this formula. So, but you see that it has exactly the same structure. You have the birth, the death, and the dynamics. But of course, here you keep track of all the lineage of the individuals. So of course, since you have this expression, you can introduce compensated martingale related to the Poisson point measure, and you have a semi-martingale writing for this quantity. And under the same initial condition as for zk, you can prove that the martingale is square integrable and has quadratic variation given here. Okay, you give me 1 minute to finish my copying. And so we have to remark that the total mass of hk is also the total mass of zk. That's the main point. That's the nonlinearity. So the nonlinearity here is, which is also here, is identical to the nonlinearity in the process zk. That plays a main role. And then we will do on Monday is that we will couple. So we have seen that when k tends to infinity, if that 0k converges to capital F, we will be able to almost replace the nonlinearity by a constant. And what we will do is that we will couple on the same, that means we will construct on the same probability space with the same Brownian motion, the same Poisson point measure, some branching diffusion processes, where the nonlinearity has been replaced by this quantity lambda. Okay? And then what we can do, and especially we will use a spinal construction, on the branching diffusion process, you will try to prove that it's very close to what you observe when you have this process with competition. Okay, and I now introduce the similar construct as the solution of the similar stochastic differential equation. So a process, branching diffusion process at tilde k, which has exactly the same expression as zk. So when I put tilde, it's related to the branching property, okay? And we can prove exactly in the same way if you have the same initial conditions that zkt will converge to the solution of the linear version of the previous PDE, where you have replaced the nonlinear part by the quantity lambda, okay? And then you will prove that this integral of f with respect to z tilde k is close to lambda. And from that, you deduce that you have this coupling between zk and z tilde k. And in the same way, you can also have a coupling for the historical processes. Then, on Monday, because the nonlinearity is identical. Okay? And then here you have the historical branching diffusion process. And we will see it's another way to, and we will play with this process and the relation between that and the spinal approach studied by Jean-François is here, donc Jean-François with Vincent, Ansel, Laurence Marsal and Ran, but also Hardy and Harris, and more recently by Aline Marguet. And we will see, so you have two visions, but which in this context are very close.
Yes, I'd like to ask a question. You showed these nice pictures before. Could you, so the pictures with the periodic pattern, could you make the relation with
which picture?
The picture with the periodic pattern.
No, that's the next. That's
okay.
I think in the
next
third or fourth.
Okay, good, thanks.
So that's related to the first picture I showed. To reconstruct the lineages of individual pickup at random in a population which seems to be at equilibrium.
Okay, I see.
Any other questions? I have a quick question. Since you, in the last, to get this nice control of the nonlinearity, you sort of assume you start in equilibrium, right? Because you start traditional measure at the equilibrium. So I'm not supposed to imagine this is some kind of long time limit. I mean, it's not long time in your picture, but in some other
from the individual, from the PD point of view, you are in a long time behavior. You are at equilibrium all the time. But the question is, what does it mean for the individuals which are underlying? Because it seems you see, you have seen your equilibrium. You have the mode at -c, but you know that it's not the optimal trait. The optimal trait in this moving framework is 0. Okay, since you have the death rate, which is x squared over 2. And so it seems that your population, you have a mode at -c, the trait -c should be the best adapted. But since the environment is changing, even if you don't see it because you are in the moving framework, the individuals, they all come from the tail of the distribution. That means you have, it's necessary to keep the tails of a distribution, imagine plants or in agriculture, because like if you only keep the mode, you can disappear very fast.
So it's like a finite time picture in a much bigger PD long-term picture.
So we will see, because so on Monday, we will consider, so what I gave you, the picture I gave you at the beginning, this picture. So here we will fix sometime t, so the people who know the spinal approach know about what I am speaking, and we will consider the reverse, at least first the trajectories in the instant, but also the reverse trajectories. And we will see a main property that I don't say for the moment. I need to keep a mystery, but essentially the reverse trajectories, they don't depend on this time t, capital T, and it's a source, so you can imagine that you go very fast in the past. So you will, and here that, of course, that depends on the fact that here you have. So you see that the mode is here and the optimal trait is here. And in fact, we will see that the equation from here going to the trait of the ancestor will be some trajectory going to 0. In fact, in our final basis.